Kia ora and welcome to video 16 in the series Delightful Differentiation. Today's problem, we're going to look at quite a tricky optimization question involving a pulley. So if you have a read through that, we've got the French fella L'Hopital, who I referenced in an earlier video, I believe, L'Hopital's rule. He's back at it. We're trying to find the length ED there, and the maximum length of ED apparently occurs when x is equal to that expression there. So as I said, it's quite tricky. I think the differentiation is pretty straightforward, but the actual solving is not. There is a clue in the actual setup of the diagram, so think about the practical elements of it. It might help you with the solving. Otherwise, the solving kind of blows up a little bit. So good luck with this, and we'll catch you after the intro music for the solution. Okay, so we've got a pulley attached to the ceiling of a room at a point C by a rope of length R, so R is constant. Another point B at a distance D from C, that's constant. A rope of length L is attached, assuming that the rope doesn't expand, that's constant. Pass through the pulley at F and connected to a weight W. The weight comes to rest at its equilibrium position, and according to L'Hopital, this is where ED is maximized. So we need to find an expression for ED, which is this length coming down the middle here, and then we need to optimize it and find the maximum of it. Okay, so it's important in optimization questions to know what is variable and what is constant. So in this question, x is the variable because that is the horizontal position of the weight when it comes to rest. ED will be maximized. We need ED in terms of x. D, the distance between B and C, and R, the length of the rope, constants. Okay, ED. Writing that as an expression in terms of x, well, we use Pythagoras to find EF, and then we add on FD. Okay, so EF, according to Pythagoras, is the square root of r squared minus x squared. And then the length FD, well, we're told in the problem a rope of length L is attached. So the length here adds up to L, and we can use Pythagoras again on the triangle on the left hand side to find BF, because remember that this here was the square root of r squared minus x squared. So Pythagoras on BEF, the triangle BEF, we can square d minus x, square the root r squared minus x squared, and then square root. This side here will be the square root d minus x all squared plus r squared minus x squared. Okay, and then because BFD, the length of that is L, a constant, and all it does is get split in different segments based on the position of F. This length here, FD, must be L minus BF. So d minus x all squared plus r squared minus x squared. Okay, so that's our FD plus L minus this. I'm going to expand all that stuff underneath. We've got d squared. We've got minus 2 dx. We've got an x squared, but we've also got a minus x squared, so they cancel, and then an r squared. Okay. So we've got some constants in there. We've got d's a constant, we've got r's a constant, we've got l's a constant. The only variable there is x. And so if we can differentiate this, let's just call it y for simplicity, then dy dx using the chain rule, r squared minus x squared all to the power of a half. So 1/2 r squared minus x squared to the negative 1/2 times by the inner derivative of minus 2x. Being careful that you don't write r squared differentiating to 2r, because r is a constant. I think I've said that a few times in this video so far. L is a constant, so that disappears when we diff. And then we got minus 1/2 d squared minus 2dx plus r squared, all to the negative 1/2, multiplied by the inner derivative of that expression, which is minus 2d, because we're differing with respect to x. Okay, now we want to make this equal to 0, because at a min or a max, we're going to get a stationary point, gradient equals 0. Tidy up this stuff a little bit, the 2's cancel there, the 2's cancel there, and we're left with minus x over the square root of r squared minus x squared. Notice I'm putting the negative power back down into the denominator as positive 1/2, or the square root. And then the other term is actually a plus. There's a negative in the front and also a minus right at the end there. Be careful with that, because otherwise you won't be able to solve the problem. 2 minuses. So we've got d on the top there, square root d squared minus 2dx plus r squared. That equals 0. 2 terms, so we can move one to the other side, then cross multiply. So let's go with the first term. We'll move it onto the other side. D over the square root, should have just copied and pasted that, never mind, equals x over square root r squared minus x squared. Cross multiply and then square both sides. So we'll end up with d squared times r squared minus x squared. The square root will disappear. And then we'll end up with x squared and d squared minus 2dx plus r squared. Again, the square root disappears. Now, this looks quite complicated. We're trying to solve for x. We're trying to find a position where this system will be at rest, and therefore, what did he call it? Equilibrium. The equilibrium position. We're trying to identify that. Show that the system reaches equilibrium when x is equal to this expression. So it looks like a messy expression. It kind of looks like quadratic formula, in that you've got a square root in there, and you've got a fraction, which is like the over 2a part. And if we look at this equation here, it is a quadratic in terms of x. So I can rearrange this equation, make it in terms of x. How we do that? Let's go 0 equals, we've got d squared x squared on the right, and we've got minus d squared x squared on the left. So if we move that to the right, we've got 2d squared x squared. We've got a d squared r squared. That's a constant, so we'll leave that to last. The linear term on the right hand side is minus, oh no, it's not a quadratic, it's a cubic. Okay, that changes things. We've got an x there, an x squared there, and another x there. Okay, so we're not going to rearrange like that. We need to think about how we solve cubic equations. Normally, there's an easy solution, and then we factor it out, and then we solve a quadratic. Like, we don't have a cubic formula. Well, there is one that exists. It takes a few pages to write it out, but we don't actually have one in our exams. So, is there a trivial solution to this problem which we could then factor out? And it turns out the diagram helps us with this. If we make x equal to r, and just think about the ramifications of that. No, we can't make x equal r, because x is the adjacent side of that triangle, r is the hypotenuse. What about making x equal to d? So moving the point E right to the left hand side, so that BE is 0 and EC is D. That would give ED is equal to L. It wouldn't be an equilibrium sort of position, but it would be the, let's just clear all this, it would be ED hanging down here. So that's probably a trivial solution to the problem. Let's see if that works. Can we make x is equal to d in this expression? Note that x equals d. Because that would mean that the left hand side, well, let's do this in a different colour, would be d squared r squared minus d squared. And the right hand side would be d squared d squared minus 2d squared plus r squared. And notice how that's equivalent. So x equals d is a solution to this cubic, and if we can factor out, therefore x minus d, we can factor out that factor and then solve the quadratic for the other two solutions. Alrighty, so that makes this problem quite tricky. How do we solve a cubic? Well, we need to know one of the solutions, and often the trivial solution to a problem where if you're trying to find the maximum volume of something, well then you can sometimes look at the minimum volume. We're trying to make the gradient equal to 0 here, so we're going to find min and max problem. Okay, so let's go to our cubic, and actually we'll make it equal 0 again, but this time we'll recognize there's a cubic term. The cubic terms on the right is minus 2dx cubed, so I'm going to put that on the left just to avoid the negative. So it's going to be 2dx cubed. So we've got d squared plus r squared. What way am I moving this? No, I'm moving it to the other side. So it's going to be minus. There's a d squared times minus x squared, so it's going to be minus 2d squared x plus the, gosh, my solving's gone to poop in this video. Gosh, that's a minus r squared all times x squared. Alrighty, and then we've got a linear term, have we? Nope, no linear term, and we've got the constant term, which needs a little bit more room for. Got a d squared r squared on the left, and that's the only constant term, equals 0. Factor out x minus r. No, it wasn't, it was x minus d. And we've got 2dx squared is the cubic term. If we expand that just to check, we'd get 2dx cubed minus 2d squared x squared. So actually that's made this term here, and it's also made that term there. The next thing is we need a minus r squared x squared. So if we go minus r squared x there, again expanding this, it would be minus r squared x squared, which is that term there, and it gives us plus dr squared x, which we don't want. There's no linear term in this expression, so to get rid of that dr squared x, we need to go minus dr squared there, close the brackets off, and then the last term will be minus d times minus dr squared, which is plus d squared r squared. So it is a factor, there's no remainder needed, and we know x doesn't equal d, so we're going to have to solve the quadratic here. X equals minus b, so r squared plus or minus b squared, so minus r squared all squared, minus 4ac, so 4 times 2d times minus dr squared, all over 2a, which is 2 times 2d. Tidying this up and taking the positive root, think about why we take the positive root here. The stuff underneath the square root becomes r to the 4. 2 negatives is a plus, so plus 8d squared r squared, all over 4d. And then just check what are we trying to aim for. R squared plus 8d squared. Okay, r squared plus 8d squared underneath the third is a common factor in these two, in the expressions here, of r squared, which means we can factor it out of the square root. When we take r squared out of the square root, it becomes r. And we're left with r squared plus 8d squared. And there's another common factor in this expression of r. So r times r plus square root r squared plus 8d squared, all over 4d. And I have a feeling that expression's written in that format, so it's a little bit disguised, and we actually have to think about how to get to it, but that is the correct answer. Another way of doing this problem would have been to take this expression here, which we were given, and substitute it into the derivative expression up here and just verify that it makes it equal to 0. That doesn't really prove that it's a maximum length, but I think it's fairly okay to reason that x equals d gives a minimum length for ED. ED is going to be longer if the weight is moved towards the center of the position. If the weight is to the left, like I highlighted earlier, sorry, in this bit here, the length ED is shorter. So hopefully that made sense. Quite a tricky optimization problem. Catch you in the next video.